Okay, good morning, everyone. This is the last demonstration for week 5, and let's see what we got for today. All right, what we do today is just practice. So we want to make sure everyone knows how to solve the truss structure. That is, of course, truss is a important um, structure type which you commonly will be dealing with in your future job. And from assessment point of view, in the mid-semester exam, that is a part of mid-semester, and also two of your practicals worth of 20%, they assume that you have a sound knowledge of the truss analysis. So let's get this right and make sure everyone um, is capable of fulfilling the expectation. Okay, so first, nothing new. That's only going to be demonstration. First, we go to page 263, and here I think we did um, all these problems yesterday. So instead, I could go to page 64, 65. All right, so let's start with problem 5-17. So in 17, we are seeking GFD, GD, and CD. So let's see how this will be done. So these are the forces in GF, GD, and CD. Okay, so that is, do you have any suggestion? What technique should be used? Do I need really to find the reactions, or can I do it in a shortcut way? GF, GD, and CD. First of all, um, I mean, this structure can be simplified, only, but that simplification, even without simplification, we can solve it. That is not what question is being asked, but you know that two members here, they are zero force members. These are DF and BH. They are zero force member. But then to find these three forces, I want you to give me a suggestion. What technique should I use here? Morning. Method of sections. Okay. Method of sections where? Yeah. Method of sections is a good option. Um, that is, you can cut through these three members. And given that this is a Gothic structure, we know that the geometry is kind of complex, but we know how to handle it, right? So, um, first thing, I need to find this angle because um, if I extend that member and then I extend this member horizontally, when they collide, they make the same angle as this one at the top, right? All right. And why do I need that? Because later on, when I cut through this one, I get a force through the CD, and rotation of CD with respect to the G, that can be done easily if I know the shortest distance between G and CD. So let me use a different color. So I'm telling you the challenge for solving this problem is to find that length, the red one. Why? Because when as I suggested by Nguyen, we make a method of section through these members, right? And when I do that, no reaction on the right hand side. It is only the 13 kilonewton, and then I get three unknown forces, CD, DG, and FG. These are the forces we want to find, right? And three unknowns, three equations. So systematically, it shouldn't be any problem. But when it comes to solving this, and well, the best rotation point will be point G. If I take rotation with respect to point G, that would vanish the two forces here, but then the CD make a rotation with respect to the G, and then you need that red length. If you don't see it now, let me just cut the structure and then we take it from there. All right. So let me um, do the method of section first. So here I'm going to cut this from here, here, there, and I'm keeping the right hand side part of the free body diagram, and that is what we really want to solve. Okay, what it takes to solve this one, I have to include the internal forces, because once you cut through the members, the internal forces have to be exposed. So you get one force axially here, you get another force, internal force here, and you get one force here. So anyone can help me with labeling these forces. The one at the lower one, what should I call this? F, GF, and this one should be called F, DG, and this one should be called. All right. So, is this solvable? Yes, it is solvable because it's a rigid body, three useful equation, and three unknowns. But then, what would be the best rotation point? One rotation point is point D, which is simple, right? Point D is simple because then you would resolve 13 kilonewton into horizontal, vertical, and then everything is doable. But the next rotation point is where? G. If I take G, then how do I find the rotation of DC with respect to the G? Look, if you want to find rotation of DC with respect to the G, you have to find the shortest distance between the force and that. And this is a red line. All right. If I have the red line, things are easy. Or the other thing I can do is FDC, I can break that into Cartesian component, and then I don't need to find the red distance. I treat that as two force. If I want to treat this as one single force making rotation, I need to find its shortest distance with the point of rotation. So I think then that's very similar to what we had in the slide Monday or yesterday. Yesterday, I think. Except over there, E was a support. You had to find the reaction at E. But here, because E has an input, I even don't bother to find the reaction forces. Just that single free body diagram is enough to find all the answers. This strategy is very important when you're solving a problem. If you get wrong strategy, the chances are you're doing too much job, and with too much calculation, the chances to make a mistake. All right, so let's start with finding that distance of the red. So meanwhile, I can easily break that force into two components. When I say easily, that is because the triangle is just made for, look at the numbers. 13 is at the hypotenuse, and 30 is the total force. So when you are breaking this force into two components, you have to break that into a vertical and a horizontal, right? So vertical is 13 multiplied by cos of this angle is 12 divided by 13. So that makes the vertical equal to 12. And the horizontal becomes 5. So now this doesn't exist anymore. Everyone happy with that? All right. So the next step, if I find that red distance, life would be very enjoyable. So here I'm making the little triangle for clarity here. All right, so that dimension is 1.2 take away 0.9. That's 0.3. And from here to there, that is 1.2. So this angle, I call this theta, and that is the same as this angle because these are similar triangles, right? And then I call this point S. So now in this triangle, call this point M, for example. So, sorry? 0.3. because from this line to the top is 1.2 meter, and then from the same line to this point is 0.9 meter. That's the difference. So now all I need is have to find GM. Okay, tan theta is zero point 0.3 over 1.2, which is 1 over 4, right? And that is equal to h over h over that distance here, which we don't know. But then how do I find? All right, so okay, with this larger triangle, with the triangle SGC, you can simply find SG. So SG divided by, or sorry, GC divided by SG, that is tan theta, which is equal to 1 over 4, right? And therefore, SG is 4GC. So SG is equal to 4 times 1.2. That's 4.8. Okay. If that's 4.8, then tan theta is, or this time sine theta. Sine theta is GM divided by GS or SG. And what is sine theta? I can find what sine theta, that is 9 plus 1.2 squared plus 0.3 squared, and root, that is, let's do it again. 1.2 squared plus 0.9 squared root, that is 1.5. So that is 1.5. And therefore here I get sine theta is equal to 0.3 divided by 1.5, and that is equal to GM over SG. SG is 4.8. Sorry? GM? Yeah, that's in this triangle. Look, at the large triangle here, at this large triangle, in this triangle, sine theta is equal to GM divided by SG. Yeah. All right? Okay, GM is 4.8 times 0.3 over 0.1, that is 1 over 5. 1 over 5. So that is 4.8 divided by 5. Okay, now we know that to be 0.96. So that's a very important number. GM is the very important number. That is the length of this red line. And now we can solve this free body diagram. How that is, just let me extend this line, and then if I extend that line, they are colliding at point G. So if this is point G, from point G, you draw a normal to that one. And this is equal to 0.96. All right, now this free body diagram is easy to solve. What point of rotation you suggest? Let's take rotation with respect to point G. So that would have zero rotation due to the GF and DC, but it has a positive rotation due to the FDC. So that is positive FDC, and the arm of rotation is 0.96. And then there are two more forces. 12 with respect to the G. What is the distance? That is 1.2, 1.2, that is 2.4, and that makes negative rotation. Minus 12, the arm of rotation is 2.4. And also 5 doesn't make any rotation. Why? Because 5 is passing through point G. Can you see that? Anyone? You see that here 5 is passing through the G. It won't make any rotation. So that's very, very simple. FDC is 12 times 2.4 divided by 0.96. So that is 30. FDC is equal to 30 kilonewton. And is this tensile or compressive? Tensile, because initially we assumed that was tensile and we got a positive number. All right, the next one is easy. The next one is, let's take rotation with respect to point D. Okay, now the next condition I apply is net rotation with respect to point D equal to 0. And you know why? Because D is the point two unknown forces are colliding at that point, that they don't make any rotation then. So if I take these two forces vanish, the rotation due to those vanish, and then the rotation of FGF with respect to the D, that's a negative rotation. That's minus FGF. And the arm of rotation is FG. FG is 0.9. And what else? 12 with respect to the D. Does it make positive or negative? That's a negative rotation. Minus 12 times 1.2. And what about 5? 5 make also a negative rotation. But the arm of rotation is from here to there. That is, sorry, this is 1.2, this is 0.9. 12 times 1.2, that is minus 18. And 5 times 0.9, that is minus 4.5. That is equal to minus 22.5. And then 22.5 divided by 0.9, that is 25, but that's negative. FGF is minus 25 kilonewton, right? All right, so now we found FDC, we found FGF, and only unknown force is FDG. To find FDG, okay, to find FDG, you can project the forces in the vertical direction or in the x direction. Maybe in the x direction is easier. Do you have any other suggestion to find FDG? Well, FDG, we can find this if we take rotation with respect to the S, but then we need some geometrical calculation. So here, I think the easiest one is net forces horizontally equal to 0. So if I apply net forces horizontally, FDC horizontal, that would be minus FDC 30 kilonewton. And that horizontal should be time cos theta. Cos theta is 1.2 divided by 1.5. Yes? That is 45. Is it? Which one? This one? 1.5? It's not 1.5. 1.2 squared plus 0.3 squared. Oh yeah, you're right. That's root is 1 point. Yeah. Okay, too late. we already. That's just one more time. That's 1.2 squared plus 0.3 squared. Yeah, I made a mistake there. But let's assume. I mean, just a procedure. Let us follow the procedure. Sorry. Um, we do the same problem in the next demonstration. So let's. So here you just simply project all forces horizontally, and then I think it's useless if I continue that solution because we made a mistake before. Let's, if that's clear to everyone, the last unknown is FDG, and if you project all forces horizontally, that would be the only unknown in this free body diagram, and that is solvable. Let's move to the next one, that is problem 18. 18 is the same structure, but it's asking for different um, calculation. 18 is asking about BG, BC, BG, BC, and HG. So that requires to cut this from here, right? So in the second problem, here we want to make method of sections here. All right. Okay, if I apply method of section here, there will be two free body diagram, left hand side, right hand side. Which one you reckon would be easier to use? Left would be easier, right? But that's required to find the reaction at A. I don't think there is any easier solution. If anyone thinks there is an easier, just let's discuss it. So again, we have to find the reaction at here, and then to find the reaction, I have to solve the entire structure. To solve the entire structure, you get one reaction at G, two reaction at A, and here we know that the components are 12 and 13. So this is 12, that is 13. Sorry, 12 and 5. All right, so this is obvious that this reaction is equal to 5. These are the only horizontal forces in the free body diagram. And then to find AY. Yes, to find AY, because these two forces are symmetrically apart. I think that the direction of the force should be downward, right? Because now they are making a rotation. The only way that rotation can be handled, I mean, you get a negative number for that. Just to avoid that negative number, let's reverse this direction. Okay, AY times 2.4 is equal to 12 times 2.4 when you take rotation with respect to the G. So rotation with respect to the G equal to 0. That AY is equal to 12 kilonewton in the downward direction. All right, now we are ready to apply method of section here, right? And then still we have to, maybe this time, instead of the method of finding the shortest distance, we resolve the forces in BC into two components. But still, I need to solve that triangle. This little triangle should be solved. So that is BC, and that is theta, and that is 0.3, and this is 1.2, right? So maybe no point of using the fractions, because these fractions are not round. So instead, I would express the angle, calculate the angle. So 0.3 divided by 1.2, that is 1 over 4. 1, sorry, this is 0.25, 1 over 4 is 0.25. Inverse tan, so this angle is 14 degrees. 14 degrees. So if this is 14 degrees in the free body diagram, um, so we want to solve that free body diagram. All right, so the forces should be included here, and here we're going to have one force here, one force here, and one force there, right? So also we need to find that angle. This angle also have to be found. Later on we do that. This is called FBC. This one is called FBG, and this one is called FHG. So let me break this force into two components. The horizontal one is FBC cos 40 degrees, and the vertical is FBC sine 40. And therefore this force 14, yeah. Yes? 14, yeah, 14. All right, in that case, if I take the center of rotation as G, so if we take center of rotation at G, net rotation with respect to point G equal to 0, these two unknown forces, they won't make any rotation, but then FBC, the horizontal component, that has a negative rotation, that is minus FBC cos 14, that is 0.97. And the arm of rotation is 0.9. Also, the vertical component would make a negative rotation, that is minus sine 14 0.24, minus 0.24 FBC, and with the vertical, the point of rotation is 1.2. And 5 is passing through point G, so 5 won't make any rotation, and 12 is making a positive rotation. So this is plus 12, and the arm of rotation is 1.2, 1.2, right? That's 2.4. So let's solve this one. Point 0.2 times 1.2 plus 0.97 times 0.9. That is minus 1.16 FBC is equal to minus 12 times 2.4, 28.8. So here FBC is 28.8 divided by 1.16, which is 2483. Okay, now if we take rotation with respect to point B, if you take rotation with respect to point B, uh, these two unknown forces won't make any rotation. FHG make a positive rotation, that is plus FHG, and the arm of rotation is 0.9. And then 12 is making a positive rotation, plus 12, and arm of rotation is 1.2. 5 make a positive rotation, and the arm of rotation is 0.9. So that is minus 21. FHE is minus 21. So that is in compression. Let's recalculate, making sure no mistake. 5 times 0.9, that is 4.5. 4.5 plus 18 divided by 0.9. Yeah, 25 or 25, yeah, 25, minus 25. All right, next step, FBG. Um, how do we find FBG? FBG, we have to resolve that into two components. Okay, so FBG, we need to know that angle, this angle has to be calculated. I call this angle alpha. So to find that alpha, this is 0.9, and that is 1.2. So 1.2 divided by 1. So that inverse tangent, that's 53 degrees. Alpha is, okay, now we know that angle. We could apply the net forces horizontally equal to 0. So net forces horizontally equal to 0, that is FBC cos 14. FBC is, that is positive, 24.83 cos 14, and then FBG sine alpha, that is also positive, FBG sine 53. And then FHG. FHG, was it positive or negative? FHG, where did we find it? Yeah, that is minus 25. Minus 25, that's negative. Minus 25. And then finally, what other horizontal force we have? Positive 5, correct? So this has to be solved. Um, 0.8. Okay, so that's 24.83 times 14 cos is 24.1 plus 0.8 FBG minus 20 is equal to 0. So that is 0.8 FBG is equal to minus 4.1, correct? So FBG is minus 5. Zoom, make it larger. Yeah. Okay, so this is a whole truss, and I mean we can discuss the steps for solving this truss structure. Okay, so that's a very important practice. If we know what steps should we take to solve a problem, without doing any number crunching, we could discuss the solution steps. So here, that's a very complex structure, too many members. If you want to find GF, GF, CD, and GC. Well, GC is a zero force member. Can you see that? Because GC is a zero force member, you have to find the forces in GF, CD. Okay, you only have to find forces in GF and CD. It's not asking about the GD. So I think the process for that is if I cut through these three members, that should be solvable, isn't it? Because it gives me three forces, provided that I know the reaction at E. But yeah, this problem has a trick. The trick is you have to make a distinction between the reaction at E and the 2 kilonewton over there. 2 kilonewton is an external load. So to find the reaction, you have to release E and expose EY over there. Do you want us to try that? I mean, I can definitely do the free body diagram for you. So with this 2 kilonewton at A and E, these are external forces. These are not the reaction. So you want to find the reaction, you have to release them. You get one force here and two force here. Of course, no horizontal force. And therefore, given the symmetry of the structure and symmetry of the load, you see both load and geometry are symmetric, correct? So if I add all these numbers together, that is 2 plus 5 plus 5 plus 5 plus 2, 4 plus 15, that is 19. So that is 19 divided by 2. This is 19 divided by 2. So 9.5, 9.5. So that is easy. And then once you make that free body diagram, you get, sorry? Sorry, say it again. On the left, have to cut it here. So let's see what question is asking. The question is asking, I'm doing this one. Yeah, this one is asking for these forces. Maybe the other one has some complication. I don't know why this is a star equation. This is not a star equation, because to me this structure is symmetric, and if you find these forces, they will be the same as the other side. But anyway, let's discuss the one 19. Let's discuss 19. So if I take the right hand side free body diagram, there will be one, two, three forces. All right. So is this solvable? Yes, it is solvable, and that is not as difficult as the Gothic structure because it doesn't have a punch. The geometry is simple. I think that is easier than the one we did before, because the one before is a Gothic. At F, you have a not 180 degrees, you have a hunch, and that geometry makes things too many resolutions of the forces and arm of rotation calculations. So that one, once you take the rotation with respect to the G, you find FDC. Once you take rotation with respect to point D, and then you find FG. So only thing you have to calculate is that normal distance here. So I think that normal distance you easily can calculate, can't you? Because this angle is workable, and you have this hypotenuse, so that you can easily find. This is a relatively easier problem compared to the previous one we did. All right. 22, 24. Okay, let's do 22. All right, what do we want to find here? That makes a big difference, okay, in deciding how you want to solve it. That is CDLDKL. CDLDKL. So that, what is your suggestion? I want to find CD, DL, and KL. What technique should I use? Method of section. But before that, maybe we have to find one reactions. So if method of section, we want to keep the left-hand side free body diagram, we find the reaction at A. So what is reaction at A? Or this is not, careful, this is not symmetric. Why this is not symmetric? Because of that 4.5 kilonewton. If 4.5 was not here, we could easily add these forces and divide that by 2. That was the reaction at the bottom. But this is not the case now. All right. So I just release the structure from the support. And obviously, here I'm going to have one horizontal, which is 4.5. And then you will have, okay, we are only interested in AY, and therefore I'm taking net rotation with respect to the G equal to 0. And that is with respect to the G. 5 times 5 positive, and then 7.5 times 7.5, that is also positive. And then we have 5, that is a positive rotation, times 10. And 4.5 make a negative rotation. Arm of rotation is 7.5. And finally, you have one negative rotation, AY times 15. So that is 25 plus 50 minus 4.5 times 7.5 divided by 15. That's 6.5. AY is equal to 6.5. Okay, let me remove that. If you have already taken note from this, that was the calculation of the reaction. Just making more space for. All right, now we just make a section from here. So one force here, I call that FLK. One force here, calling that FLD. And one force here, termed or labeled as FCD. So all these forces, they assume they are in tension. The members are tensile members. And we could take the rotation with respect to point D. If I take rotation with respect to point D, so that take care of these two forces. And then you have FLK making a negative rotation minus FLK, and that is times 2.5. And 5 kilonewton with respect to point D, that is a positive rotation, plus 5, and arm of rotation is 2.5. And 4.5 make a negative rotation. And finally, 6.5 make a negative rotation. And that is 7.5. Five minus 4.5, that is 2.5 times 0.5 minus 6.5 times 7.5 divided by 2.5. 19. I got FLK equal to 19. 19, yeah. Uh, let's check out. That is positive, negative, negative. I take that here. It becomes minus negative. You're right. So that is minus 19. Minus 19. Next, we take rotation with respect to point L. With respect to point L. So with respect to point L equal to 0, that would take care of four forces together, right? So that's a very convenient point. And then FCD make a positive rotation. That is FCD multiplied by 2.5, positive. And then 6.5 make a negative rotation, minus 6.5, and the arm of rotation with that is 5. Therefore, FCB is that's 13. So this is tensile. FCD becomes tensile. And finally, to find FLD, that is simple. You have to either find the forces horizontally or vertically equal to 0. So let's take the forces horizontally equal to 0. So that is minus 19 plus 13 plus 4.5 plus FLD cos 45, and that's it. Uh, this one, 19, 13, that cos theta of 4.5. These are only horizontal forces. It's a horizontal force. Huh? Yes? All right. Cos 45. Yeah, horizontally that would be, if, yeah, it is the same. 45, 45 won't make a difference. That is equal to 0. So 19, 13, that is minus 6 plus 6.4.5, that is minus 4.5. Yep. 1.5. 1.5 negative. So take it to the other side. 1.5 divided by cos 45. 1.5 divided by 45 cos. That is 2.12. Is that what you got? Yeah, 2.12. And that is tensile. So that was 21. What else do we have? 22. Let's go to 24, 27. Okay, two more questions. Let's discuss about the strategy. What strategy is needed to solve this problem? What technique and what steps? Do I need to solve the reactions? Yes, one of the reaction is enough, right? And if we choose to keep the left-hand side free body diagram, only we need Fy. So let's do that first. Um, so I take rotation with respect to point A equal to 0. And that is Fy multiplied by 4. That is negative. Minus 4Fy. And then 40 kilonewton makes a positive rotation. That is plus 40 times 2. 50 kilonewton does not make any rotation because it passes through A. 30 kilonewton make a positive rotation. That is plus 30 times 3. And also 40 kilonewton make a positive rotation. That is plus 40 times 1.5. That's 230 divided by 4. Fy is 57.5. Yes. So making more room here. Let me remove that or bring this down. Um, now, now what? Look, you only need three forces to be calculated, and for that we don't have to solve all the members, only three members. So that sounds like method of sections. Method of sections, that is when you want only few forces, and the section goes through ED, EH, and GH. Um, so So here in this grid by diagram method of section applied to this member, you get three forces: FED and FEH and FGH. So there are two natural conditions which simplify the solution. The first is rotation with respect to the E equal to 0. Rotation with respect to the E equal to 0. So that takes care of three forces here, and then I have FGH making a positive rotation, and the arm of rotation for that is 1.5. And Fy makes a negative rotation, that is minus 57.5, and arm of rotation is 2. So that multiplied by 2 divided by 1.5, you get FGH equal to 76.7, and that is tensile. Then the next natural condition to apply, which point of rotation would be next? Uh, that would be H. Yes, H is the next point of rotation because two forces collide over there. And let's apply that condition. Net rotation with respect to the H equal to 0. That is FED makes a negative rotation, minus FED, and arm of rotation for that is 1.5. And 40 kilonewton make a positive rotation, arm of rotation is 2. And finally, 5.7 is a negative rotation, arm of rotation is 4. FED is 10, 100, 100 negative. That is in compression. And finally, FEH, we can find that by just, I need to know that angle. Or this angle. So alpha is 1.5 divided by 2 inverse tan. Sorry? 37. 1.5 divided by 2. 36. Sorry? Yeah, almost 37. Almost 37. And now we can write the net forces horizontally. So net forces horizontally equal to 0. That is minus 100 plus FEH cos 38. Was it 38? 37. And plus 76.7. And that's it. These are the only horizontal forces. 76.7 minus 100, that is become positive, divided by 37 cos. 29.17, is it? And that is positive. All right, the last demonstration we have for today is this one. And let's just get into it. So what do we want to find here? Let's check out. That is BC, HC, and HG. Well, that is pretty much like a Gothic structure because it has a hunch at this joint H. So that makes the geometry very complex. I mean, apart from that, I don't see any point with this problem. So let me emphasize the importance of the Gothic. Um, we have gone through, this is not for the exam. This is not for the exam because you know it takes lots of calculation. But with your practical 1 and 2, that's the type of structure we deal with. And over there, you have to do hand calculation, and your hand calculation can be checked by web solution. So I give you a link. There is a Italian website which lets you to solve the 2D truss structure. You build your truss over there, put the forces, and it calculates the forces for you. So that's we do the hand calculation, web calculation, and experimental measurement, and that's give you a room to discuss the errors in the experiment, um, and that's the only thing. So here I only discuss the strategy, the steps. So this structure doesn't seem to have any zero force member, right? C, B, D, they are not zero force member because they have external forces on them. But to make a section through BC, HC, and HG, you need to solve the left-hand side free body diagram. For that, we need to solve the reaction at A. And that is not difficult. Just the only thing which might confuse you is those external forces, they are different with the reaction forces. So you put them in the free body diagram and then exposing AY, EY, that is the free body diagram you have to solve. I think that's enough for today. Just if you just bear with me for attendance, we'll be good to go.